Welcome to the Walton Pi. In this video, we are going to go over the proof of the binomial theorem. In the previous video, we stated what the binomial theorem was, as well as a few examples, and in part 1, we went through the basics of the different aspects that we would need to understand in order to complete this proof. So, the statement of the theorem is that x plus y to the n is equal to the sum from k equals 0 to n of n choose k times x to the n minus k times y to the k. Now, we are going to go through this proof by way of induction. So, to start off, we will have our base case. Here, our base case is when n equals 0, so we get that x plus y to the 0 is equal to 1, which is going to be equal to the sum from 0 to 0 of 0 choose k, x to the 0 minus k, y to the k. The base case is fairly straightforward. The complicated part we'll get to when we go through the inductive step. The inductive hypothesis is where we get to assume that for some m greater than or equal to 0, x plus y to the m is equal to the sum from k equals 0 to m of m choose k, x to the m minus k times y to the k. We will then be using this in our inductive step in order to show that it will also hold true for m plus 1. So, if we start with x plus y to the m plus 1, we can pull out one term of x plus y. So we get x plus y times x plus y to the m. We can split this up via addition, and we get x times x plus y to the m and y times x plus y to the m. We will simplify each of these two pieces separately and then combine them later to get our end result. So, x times x plus y to the m is equal to x times the sum from k equals 0 to m of m choose k times x to the m minus k times y to the k. We can then pull this x in and increase the exponent on the x by a 1, which is where we get this x to the m plus 1 minus k in that second sum. For y times x plus y to the m, we will have a very similar thing happen where we will have a y on the outside of the sum and we will pull it in and increase the exponent on the y, which is why at the end we get that y times x plus y to the m is equal to the sum from k equals 0 to m of m choose k times x to the m minus k times y to the k plus 1. We will use these two sums in order to try and simplify our expression. So, the sum starting at k equals 0 and going to m of m choose k times x to the m minus k times y to the k plus 1, the m minus k is the same thing as saying m plus 1 minus k plus 1, which means that this is actually now of the form of an m choose k minus 1 x to the m plus 1 minus k y to the k. Here we are doing an index shift where we are replacing every k plus 1 with k. So the sum turns into the sum from k equals 1 to m plus 1 of m choose k minus 1 x to the m plus 1 minus k y to the k. The reason that we increased our ending point by 1 as well is we needed to add up the same number of terms. So if we only changed k to go start at 1 instead of 0, we would be adding one fewer term. So that is why our ending index is now m plus 1. Thus, y times x plus y to the m is equal to the sum from k equals 1 to m plus 1 of m choose k minus 1 times x to the m plus 1 minus k y to the k. Therefore, we have x times x plus y to the m is equal to the sum from k equals 0 to m of m choose k x to the m plus 1 minus k y to the k, and y times x plus y to the m equals the sum from k equals 1 to m plus 1 of m choose k minus 1 x to the m plus 1 minus k y to the k. Adding these two together, we are going to get this sum. We are now going to try and combine these sums in order to simplify it down. The first thing we can do is we can try and get both of them to have the same starting and ending indices. So, for the first sum, we can increase our ending index by 1 because the last term is going to be an m choose m plus 1, and m plus 1 is bigger than m. which means that the binomial coefficient will be defined to be 0. So by increasing our ending index by 1, we do not change the value of the sum. In a similar manner, if we decrease the starting index of our second sum from k equals 1 to k equals 0, the bottom part of our binomial coefficient is going to be an m choose -1. We can never choose a negative value, and so it is defined to be 0 for that case as well. So we can change our starting indices without changing the overall result. Therefore, since they are both the same starting indice, we can actually now combine them into a single sum. So we now have the sum from k equals 0 to m plus 1 of m choose k plus m choose k minus 1, all times x to the m plus 1 minus k, y to the k. Now, if you watched the first video, you may recognize that m choose k plus m choose k minus 1 is really m plus 1 choose k. So, we have now simplified this down into a single thing, which is exactly the form that we were wanting it to be. We wanted to show that x plus y to the m plus 1 is equal to the sum from k equals 0 to m plus 1 of m plus 1 choose k times x to the m plus 1 minus k, y to the k. Because we successfully were able to show that here, that tells us that x plus y to the n is in fact equal to the sum from k equals 0 to n of n choose k, x to the n minus k, y to the k, for any x, any y, and any positive integer n. If you enjoyed this video or thought it was helpful, please like and subscribe as it will help me out quite a bit, and please consider watching some of my other videos. Have a great day.